Hello students, good morning. So this is our third lecture of thermodynamics. In the previous two lectures we have discussed a lot about the basics of thermodynamics and first law of thermodynamics. We applied first law of thermodynamics in solving problems in reversible and irreversible processes. In this lecture we are going to cover the further application of first law of thermodynamics, that is first law applied to adiabatic process. So today we are going to cover the first law applied to adiabatic process, or application of first law to adiabatic process. So first law applied to adiabatic processes. We discussed in the first lecture basics of thermodynamics about different type of processes, in which one process was adiabatic process. So just recall what is exactly adiabatic process to proceed today. Adiabatic process is a process in which exchange of heat between system and surrounding is restricted. Means system can neither absorb heat from surrounding nor supply heat to the surrounding. So we say that heat of the system is constant. That is the characteristic of an adiabatic process. So in adiabatic process, the characteristic is that Q is 0. Where Q represent the heat transfer either to the system or from the system, and that must be 0 if the process is to be adiabatic. Now we need to determine work done in adiabatic process as we did in isothermal process and other processes. But we know that work is not a state function, it depends on path, and therefore once again, for applying the first law to adiabatic process, in order to determine the work done, we'll have to define the path, we'll have to define the process. So again, adiabatic process will be applied differently to reversible process and to irreversible process. Moreover, the problems of adiabatic process are usually a bit tricky, and extra attention needs to be taken when solving the problems based on adiabatic process. So we are going to apply adiabatic process in determining work and related properties in reversible and irreversible processes. So we will be starting with a reversible process first. Adiabatic process which is simultaneously reversible also. To visualize it, let us consider expansion of an ideal gas. If we have an ideal gas confined in a piston at initial volume V1 and it undergo expansion finally to V2 under adiabatic condition. So it is reversible adiabatic expansion. If we apply the first law to this reversible process, we must be very careful when writing first law because it is a reversible process in which the final state is reached through infinite number of intermediate equilibria. So for an infinitesimal step, for a small step, we write the first law as du, change in internal energy, is equal to dq plus dw. But since the process is adiabatic, so this will be 0. So we have du is dw. Let us call this equation 1. If we integrate this equation on the two sides just for determining work, we obtain integral of dw is equal to integral of du delta u. So work done by the system is equal to change in the internal energy of the system. And if we elaborate it further, it is NCV delta T. NCV delta T. So work done is change in internal energy, which is NCV delta T. We also know that in case of expansion, work is done by the system. So value of W will be negative, it will be less than 0. So delta U will be less than 0. W is less than 0, therefore delta U will be less than 0. It means in adiabatic expansion there occur decrease in internal energy, which is quite obvious because energy is not supplied from outside, but system does work on surrounding. Work is a form of energy. So for doing work, system will have to expense, system will have to spend some energy, and that energy can come from the internal energy of the system only. So system transforms some of its internal energy into work done on the surrounding. So in adiabatic expansion, system does work on surrounding at the cost of internal energy, that is by decreasing its internal energy. Since delta U is negative, this implies NCV delta T is also negative, where N and CV are positive quantity, so delta T must be negative, and delta T negative means T final must be less than T initial. This indicates that when an adiabatic expansion occurs, cooling is observed inside the system. System will undergo cooling. As we all know that internal energy is directly related to temperature, and we are saying that internal energy of the system will decrease, therefore temperature must decrease, which we have proved mathematically also that in adiabatic process, if expansion occur, it occur at the cost of internal energy and the gas will undergo cooling, and its reverse will also be true. If we compress a gas adiabatically, then work will be done on the system. In that case, W will be positive, so delta U will be positive, delta T will be positive, and therefore T final will be greater than T initial. That is, temperature will increase, and it will be due to addition of the energy into internal energy due to work done on the system. So work done is delta U, which is NCV delta T. It's a important relation we will be using. But the problem is not so straightforward given to us that this is delta T, so determine work done. That type of problems are rarely found in IIT-JEE. So the biggest challenge of adiabatic process is to find out the final temperature. What will be the final temperature in case of adiabatic expansion or compression? If the process is reversible, we need to derive a relationship between P, V and T in adiabatic process, and that is derived using this equation number 1. We know that du can be written as from equation 1, this du can be written as NCV dt, and dw we have already discussed in very first lecture is dw is minus P dV, where this P is a function of V and T, so it can be written as minus nRT by V into dV. So cancel the n on two sides and rearrange this equation. This equation can be rearranged as dt upon T is equal to minus R upon CV into dV upon V. We discussed earlier the relationship between Cp, Cv and R. So this R upon Cv is basically gamma minus 1. Cp minus Cv we know Cp minus Cv is R, so if we divide it by Cv on the two sides, it becomes gamma minus 1 is equal to R upon Cv. So if we substitute R upon Cv as gamma minus 1, it will become equal to minus gamma minus 1 dV upon V. Now if we integrate the two sides by applying limit T1 to T2 for temperature and V1 to V2 for the volume, what we find on left side dx upon x form is there, so it will be log natural x. Applying limit, left side will become ln of T2 upon T1. On the right side it will be gamma minus 1, and I am taking minus sign inside the limit, inside the integration. So it will become ln of V1 by V2. Had not been minus sign there, it would have been V2 by V1. So if we take minus sign inside, it will be ln V1 by V2. Now simplify this log, bring this gamma minus 1 into exponent of this volume ratio. So it will be ln of V2 upon V1 raised to the power gamma minus 1. So ln T2 by T1 is ln V2 by V1 raised to the power gamma minus 1. This implies T2 upon T1 is equal to V2 upon V1 raised to the power gamma minus 1. So it can be generalized as V1 by V2, V1 by V2, V1 upon V2. So it is not V2, V1 upon V2. Now if we generalize it, it will be T1 V1 raised to the power gamma minus 1 is equal to T2 V2 raised to the power gamma minus 1. T1 V1 raised to the power gamma minus 1 is equal to T2 V2 raised to the power gamma minus 1. So if we generalize it, it will be TV raised to the power gamma minus 1 is equal to constant. This is an important relation for a reversible adiabatic process. I am emphasizing the word reversible. This relation will not be applicable to all adiabatic process. This will be applicable only to reversible adiabatic process, where we can write an infinitesimal step by first law du is equal to dq plus dw. It is a relationship between temperature and volume. Similar relation can be derived for pressure volume, pressure temperature. Let us derive them. So if we want to derive a relationship between pressure and volume, substitute temperature by pressure. So T can be substituted. Let us remove this now. T can be substituted as PV by NR. So if we substitute this T by PV upon NR into V raised to the power gamma minus 1 is equal to constant for a given system. N will be constant, R will be constant. So V raised to the power gamma minus 1 plus 1 for one more V. So it will become PV raised to the power gamma is equal to constant. This is another relation we use in reversible adiabatic process. Similarly, relationship between P and T can also be derived. So in this equation, let us substitute V in terms of P and T. So we can write T V is equal to nRT by P. So nRT upon P TV. We want relationship between P and T. So just 1 second. Here we have PV. So PV is equal to nRT by P raised to the power gamma is equal to constant. So P will become P raised to the power 1 minus gamma, 1 numerator, gamma denominator. So P 1 minus gamma, T gamma, n r raised to the power gamma will come in the constant side. So n and r are constant. So it will be constant. So this is the third relation we have derived for a reversible adiabatic process. I am repeating the term again and again that we can apply these relationship only if we are sure that the process is adiabatic as well as reversible. If the process is not reversible, then these relations will not be applicable as such. So that is the way we derive relationship for a reversible adiabatic process, and then we apply this in solving problems related to a reversible adiabatic process. So now let us apply the derivation we have done just now for attempting problems of IIT-JEE standard. Let us start with a simple application of first law into a reversible adiabatic process. This is our problem number 1. It is given that 2 moles of a monoatomic ideal gas, initially at 600 Kelvin in a 2-liter insulated, this is important, 2-liter insulated cylinder undergo reversible expansion till volume is 16 liter. Determine final temperature and work done. CV is 3/2 R. Heat capacity may or may not be given because we need to remember the expression for Cp, Cv for monoatomic, diatomic, triatomic gases. I have briefed this in beginning. This you have studied in very detail in physics equipartition principle. Applying the concepts of degree of freedom, you derive the expression for heat capacity for different systems. So now come to this problem. We have 2 mole of a monoatomic ideal gas initially at 600 Kelvin in a 2 liter insulated container. Insulated container means now the process will definitely be adiabatic since it is insulated. Exchange of heat will not take place. A reversible condition is already given. So it is a case of reversible adiabatic expansion. Reversible adiabatic expansion. Initially temperature was 600 Kelvin and volume was 2 liter. Finally, temperature T2 is unknown, volume is given 16 liter. Using the relations we have derived for temperature and volume in a reversible adiabatic process, this T2 can be known. We have just derived the relation that Tv raised to the power gamma minus 1 is constant. So T1 V1 raised to the power gamma minus 1 will be T2 V2 raised to the power gamma minus 1. Cv is given 3 by 2R, so Cp is 5 by 2R, and therefore gamma is Cp by Cv 5 by 3, so gamma minus 1 is 2 by 3. Now if we solve this for T2, we find that T1 upon T2 will be equal to V2 upon V1 raised to the power gamma minus 1. If we substitute the value of volumes and gamma minus 1 from there, what we find? V2 is 16. So 16 upon V1 is 2 liter raised to the power 2 by 3. It is 8. So 8 can be written as 2 raised to the power 3, that whole raised to the power 2 by 3. So 3 will cancel off, giving 2 raised to the power 2. So it is 4. Therefore T2 will be T1 by 4, which is 600 divided by 4, 150 Kelvin. This is our first result, final temperature. Now work done. In a reversible process, in an adiabatic process, work done will be equal to delta U, which is NCV delta T. N is 2, so it is 2 into Cv 3 by 2R into delta T. Delta T is 600. Delta T, be very careful, delta T is final minus initial, so 150 minus 600. This 2 will cancel off. It is 450, so it will be 450 into 3, 1350, but with minus sign. So 1350 R with minus sign. If we substitute the value of R, we can find the value magnitude of work done. So 1350 multiplied by 8.314, it is 1124 approximately, 11224. It is minus 11224 joule. 11224 joule. 11,224 joule. But minus sign is important. So this is the first problem, which is a direct problem on reversible adiabatic process. Next, we proceed further in this process with a comparative concept, that how this adiabatic process compare with isothermal process on a PV diagram. Suppose we imagine a thermodynamic process suppose we imagine a thermodynamic process one in which gas undergo isothermal reversible expansion. Isothermal reversible expansion. So the temperature here T1 will also be the temperature here, since the process is isothermal. Now imagine another thermodynamic process 2, where initial conditions are same volume, same initial temperature. Now this undergo expansion to same final volume V2, but now adiabatic reversible expansion. Here temperature is T2, which is less than T1. T2 less than T1. If we draw a PV diagram for the first process, what we see here, we have pressure, volume. This is PV diagram for the first isothermal process. This is V2 and this is V1, and area under the curve is the work done. In case of adiabatic process, the T2 is less than T1. Temperature is less in final condition and pressure is nRT by V. In final condition, volumes are same. In final condition, volumes are same in both cases. Number of moles are same. So pressure will be more in case of isothermal process, since T1 is greater than T2. So in case of adiabatic process, if expanded to same volume, the final pressure will be less. So if this correspond to P2 isothermal P2 final pressure for the adiabatic process will be below to this. Let us take that here. P2 adiabatic. P2 adiabatic is here. So the adiabatic path will exactly be like this. Work done is area under the curve on a PV diagram. So there is greater area under the curve 1 than under the curve 2, and the difference is this area. So few things can be derived here, which is very important in attempting the problems on isothermal and adiabatic processes. What we can derive here? We can derive here from this discussion that from same initial states, means P1, V1, T1 are same in both cases, to same final volume V2. Initial states are same, but final states are not same, only final volumes are same. In that case, magnitude of the work done in isothermal process is greater than the magnitude of work done in adiabatic process, which we have shown here. Also, we can see that the slope dy by dx, slope of the curve 2 at every volume is greater than the slope of the curve 1. Curve 2 is steeper than curve 1. So we can say that volume decreases more rapidly in adiabatic process than in isothermal process. So we can say that magnitude of slope of tangent magnitude of the slope of tangents is greater for 2 than 1 at same V. Meant at same x coordinate, if we find the magnitude of the tangent on the 2 curve, it will be more for adiabatic process than for isothermal process. This can be derived for the same final pressure also. Now, suppose if we have another situation in which initial volume is V1, initial temperature T1, and now this gas undergo isothermal reversible expansion to V2, but temperature is T1. Reversible isothermal expansion. In another case, from the same initial state V1, gas undergo expansion to same final pressure now, same final pressure, but now the temperature will be different since it is adiabatic. So temperature will be T2. This by reversible adiabatic expansion. Now we want to compare these two on the PV diagram. Once again, if this is the curve, if this is the curve, if this is the curve for case 1, let us call this case 1, and case 2 for isothermal process, here we have initial volume V1, here we have now final pressures are same. So let us take final pressure P2 here. What will happen to the final volume in case of adiabatic process? This is V isothermal, V2 isothermal. In case of expansion to same final pressure, we know that T2 is less than T1. We want to compare their volume, and V is equal to nRT by P. Now the final pressures are same, and temperature here is less. T2 is less than T1. So T2 is less than T1, so volume in case of final volume in case of adiabatic process will be less than the final volume in case of isothermal process. So we can say that V2 adiabatic will be less than V2 isothermal, and that will be somewhere at this point. Let us call it V2 adiabatic. So now the adiabatic path will be like this. Once again the same result will come. Area under the curve 1 is more than the area under the curve 2, and curve 2 is steeper than curve 1, that is magnitude of the slope of the tangents on curve 2 is greater than the magnitude of slope of tangent on curve 1 at same value of volume. So these are the two comparisons we have done in isothermal and adiabatic process. It helps a lot in understanding the two processes thoroughly. Next, we will be solving some more problems related to reversible adiabatic process. But now we have done isothermal process in detail. Adiabatic process, we have just solved a problem. So let us combine both isothermal and adiabatic, because in exam usually we find problems based on combined isothermal adiabatic processes. So let us take that type of questions. This will be our problem number 2 of today. The question is, 1 mole of a monoatomic ideal gas. Monoatomic means CV is equal to 3/2R. 1 mole of a monoatomic ideal gas initially at state A, defined by 600 Kelvin and 8 atmosphere. 600 Kelvin and 8 atmosphere. Undergo a reversible isothermal expansion to state B. Now the system is cooled isochorically. The system is cooled isochorically, means constant volume. Now the system is cooled isochorically to a new state C, where pressure is √2 atmosphere. And then finally compressed reversibly and adiabatically to A. Determine work done and Q, drawing a PV diagram. It's a combination of 3 processes. 3 steps are involved. We can make a flow chart first for solving this problem. Here we have state A. Mole is constant everywhere, so there is no need to write mole. A, 600 Kelvin, 8 atmosphere. Reversible isothermal to state B. No information is given for state B, but we can say that since it is isothermal, the temperature here is also 600 Kelvin. Then isochoric cooling to C, where pressure is √2 atmosphere, and then reversible adiabatic to A. So this is the flow chart situation of this question. With the knowledge we have just gathered, we can depict this changes on a PV diagram as Here we have pressure, volume. Reversible isothermal expansion from some initial state A to a new state B. This is state B. Then isochoric cooling, cooling at constant volume. So as we cool, pressure will decrease. At constant volume, if temperature is decreased, pressure will be decreased. It is state C, and then reversible adiabatic compression to A. It is isothermal. It is adiabatic. We have just discussed that adiabatic curve is below to isothermal curve all the time. This is the situation. So work done exactly will be this area enclosed in this curve. It's a cyclic process. It's a cyclic process because initial and final states are same. So for solving work done in this three process, if we call this work W, it will be 0 since isochoric. So at constant volume, no work is done, no mechanical work is done. So work is done only in the first and second AB and CA steps. In steps, it is isothermal reversible expansion AB. So we need to solve first either pressure or volume at B in order to determine the work done using the relationship W is equal to minus nRT ln V2 by V1 or minus nRT ln P1 by P2. So neither pressure nor volume is known. But at C, pressure is known, it is root 2 atm. At A, temperature is 600 Kelvin, pressure is 8 atm. If we connect the point A and C adiabatically, we can find out the temperature at C. Between A and C, if we apply the relationship between pressure and temperature for reversible adiabatic process, what we have seen, P raised to the power 1 minus gamma T raised to the power gamma is constant. So, or we can say that P raised to the power 1 minus gamma upon gamma into T is constant. Now let us solve first 1 minus gamma upon gamma. Since the gas is monoatomic, gamma will be 5 by 3. So 1 minus gamma will be 1 minus 5 by 3, so minus 2 by 3. So 1 minus gamma upon gamma will be minus 2 by 3 divided by 5 by 3. So it will be minus 2 upon 5. Now use that value of 1 minus gamma upon gamma in this. Now we can write P1 raised to the power minus 2 upon 5 into T1 is equal to P2 raised to the power minus 2 upon 5 into T2. So in fact it is T1 upon P1 raised to the power 2 to 5. So it can be written as T1 upon P1 raised to the power 2 to the 2 raised to the P1 raised to the power 2 by 5, and T2 upon P2. So T1 upon T2, T1 upon T2 will be P1 upon P2 raised to the power 2 upon 5. I have taken P1 and P2 in denominator and then cross multiplied. So T1 upon T2 will be this divided by this, but negative power will become positive if we take the reciprocal. P1 and P2 are known. If we take this point as 1, this as 2, so P1 is 8 divided by root 2 raised to the power 2 upon 5. Inside it is 4 root 2, so 2 raised to the power 5 by 2 raised to the power 2 upon 5, so it is in fact 2. So T2 will be T1 divided by 2, it is 250 Kelvin. So now temperature is known at C, it is 250 Kelvin. Temperature here is 500 Kelvin. And therefore, the pressure here must be double of this, since at constant volume P is directly proportional to T. So temperature is halved, so pressure will also be halved. So temperature at B must be 2 root 2 atmosphere. This is important. 2 root 2 atmosphere. Now everything is known. We can determine the work done in the 2 step. So work done, WAB will be minus nRT A ln of P1 by P2. P1 is 8 upon P2, 2 root 2. So it is 4 upon root 2, 2 root 2. So 2 raised to the power n is 1. So it is minus R T A ln 2 raised to the power 3 by 2. If we take 3 by 2 outside the log, so it will be minus 3 by 2 R T A ln 2 ln 2. So ln 2 is 0.7, ln 2 is 0.7, so 0.7 into 3, 2.1 divided by 2, so minus 1.05 R into TA, and TA is 600. So it is 630. It is minus 630 into R. It is W of A, B. One work we have determined. Now let us determine work done in CA. WCA. WCA will be nothing but delta UCA, and it will be NCB delta T. So N is 1, CV is 3 by 2R, and delta T 600 minus 2, something wrong is going on. We have taken here 600. So if it is 600, how it can be 500? It is 600. A T2 will be T1 by 2, so it will be 300. Just slight correction in calculation. So 300, it is 300. So T2 will be 300. The rest of the thing will remain same. One more correction will have to be done here where we use temperature. So we use 600. So 600. Oh, we have already taken 600 here. So it is 600 into 1.05. We have taken 600 into 1.05. So it is 630. It's fine. Now, WCA is 3 by 2 into R into T final minus T initial. It will be 300. 600 minus 300. So 300. So 150 into 3, 450 R. 450 R. So total work will be WAB plus WCA, and WAB is minus 630 R, other is 450 R. So it will be 180 with minus sign, 180 R. So minus 180 into 8.3 joule. If we multiply it, we can find out the value of total work done. And it is negative, which is quite obvious. It has to be negative since the area under the curve isothermal is more, which is negative. Area under the adiabatic curve is less, which is positive. So resultant will be negative. This is the negative work. One more thing is asked there, that what is the value of Q? What is the value of heat in this entire process? Since this process is cyclic, so the total change in internal energy will be 0. Total change in internal energy will be 0. So if we apply first law, to the whole process, what we find, 0 is equal to change in internal energy delta U. 0, since it is cyclic process, initial final states are same, so change in state function will be 0. So 0 is equal to Q plus W. So Q is equal to minus W. So just we'll have to change the sign here. It will be 180 R. So this way we solve problems when there is more than one type of processes combined together. Let us take one more problem from isothermal adiabatic process to further accentuate the concepts behind these two type of processes. This will be our problem number 3. In this problem, the situation given is 1 mole of an ideal gas whose CV is now given 2R. 1 mole of an ideal gas in a 1 liter piston at 500 Kelvin. Is taken to a new state where temperature is 250 Kelvin and volume is 20 liter through reversible path. 1 mole of an ideal gas in a 1 liter piston at 500 Kelvin is taken to a new state where temperature is 250 Kelvin, volume is 20 liter through a reversible path. Construct a path in which gas first undergo isothermal expansion followed by adiabatic expansion to reach the final state. Depicting on a PV diagram, determine the net work done. It's a very fundamental and I can say very good question relating isothermal and adiabatic processes. We have been given an initial state. Where volume and temperature are known, and a final state where volume and temperature are known. But the final state is not reached in one single step. Final state is reached in 2 steps, 2 consecutive steps. In first step, the gas is expanded isothermally to some intermediate volume and then adiabatically, so that the initial and final state can be related by a continuous path it is better first to draw a TV diagram, temperature volume diagram, to understand the situation. What is happening here? If we have temperature on this side, volume here, this is the initial state. First, isothermal reversible expansion. So temperature is constant, volume is increasing. And then adiabatic reversible expansion. Adiabatic. In adiabatic expansion, temperature decreases. So temperature is decreasing, volume is increasing. Second will be like this. It is isothermal and it is adiabatic. Temperature here is 500 Kelvin, volume is 1 liter. Temperature here is 250 Kelvin, volume is 20 liter. Here volume is 1 liter. Since it is isothermal, the temperature here will also be 500 Kelvin. But volume here will be somewhere between 1 and 20 liters, so let that be V. Work done in second step can easily be known. Since it is adiabatic process, so work done will be NCV delta T. The problem here is to find the work done in the first isothermal step, and for that we'll have to find out the volume, intermediate volume. Then only we can apply nRT ln V2 by V1 formula. So let us correlate this two through reversible adiabatic process relationship between temperature and volume. We have seen that in reversible adiabatic process, TV raised to the power gamma minus 1 is constant. Now CV is 2R, so CP will be 3R, so gamma will be 3 by 2, 1.5. So gamma minus 1 will be 0.5 or 1 by 2. So let us apply T1 V1 raised to the power gamma minus 1 is equal to T2 V2 raised to the power gamma minus 1. So 500 into V raised to the power gamma minus 1 is 0.5, so 1 by 2 is equal to T2 250 into V2 raised to the power 1 by 2. So 250, 502. So V is what? If we solve here, V, or let us square the two sides. Squaring the two sides, we obtain 4 into V is equal to 20. So V will be 5 liters. So now we have known V 5 liter. So since volume is known here, work can be known in the first and second step. So work in the first step, let us call it 1, 2 and 3. So W12 will be equal to minus NR into temperature is 500, nRT ln of V2 by V1. V2 is 5 upon 1. N is 1, so it is R 500 R. It is minus 500 R ln 5. ln5 is known to us. Ln5 can be written as 2.3 log 5. Log 5 is 0.7. So it is 1.6. ln5 is 1.6. So 500 into 1.6, 800 R. So it is minus 800 R. Now, for the second step, W23 work will be NCV delta T. N is 1 into CV is 2R into delta T, and delta T is minus 250, final minus initial, 250 minus 500. It is N, it is CV. So minus 250 into 2 minus 500 R. So total work done will be 8513 minus 1300 R, or minus 1300 into 8.3 joule. So if we solve it, (10790) minus 10790 joule, so approximately 10.8 kilojoule. This is the total work done. If we want to describe this process on a PV diagram, if this represents isothermal, this will represent adiabatic, since slope is more for adiabatic. So this is adiabatic work done, and this is isothermal work done, and this is minus 800 R, and this is minus 500 R, and this entire is the total work done. So that is the way we determine work done, by combining reversible adiabatic with reversible isothermal process, or absolute reversible adiabatic process. After this, let us proceed to a new concept, another concept in adiabatic process itself. The next we are going to take is irreversible adiabatic process. Irreversible adiabatic processes. It is interesting to watch. We'll find some fundamental difference between reversible and irreversible adiabatic processes. Suppose we have an insulated piston. We have an insulated piston containing some gas initially at volume V1. Say helium gas is there. Now suppose if this gas undergo adiabatic expansion to a new volume V2, but this time against a constant external pressure, it is possible. Suppose we have helium gas here at 10 atmosphere. We suddenly release the outside mass on the piston, so that gas push back the atmosphere, the 1 atmosphere, till the gas pressure decreases to 1 atmosphere. So it will be an irreversible adiabatic process. In this irreversible adiabatic process, it's a one-step process. Infinitesimal step is not involved. So if we write the first law, that is delta U will be equal to Q plus W. Since the process is adiabatic, no matter how the change is occurring, Q is always 0. So it is 0. This implies W is equal to delta U, which is NCV delta T. So work done by the system is NCV delta T, and in irreversible adiabatic process, W is minus P external delta V. So if we relate this to, we find minus P external delta V is equal to NCV delta T. This is a very important relation for irreversible adiabatic process. Since it is case of expansion, so delta V is positive, P is positive, so this whole term will become negative. Work is done by the system has to be negative. Therefore, delta T must be negative, and therefore T final must be less than T initial. This implies T final must be less than T initial. Therefore, adiabatic process, adiabatic expansion leads to cooling of gas, and vice versa is established once again. Now, the difference we need to understand is that the relationship we derived in reversible process, PV to the power gamma constant or TV to the power gamma minus 1 constant, or P raised to the power 1 minus gamma, T raised to the power gamma constant, are no more applicable in irreversible process, because we derived those relations from the expression du is equal to dw. Now we don't have du is equal to dw. It's a one-step process. So the relationship will be derived from this expression only for the final temperature. How it is done? Let us try a simple straight questions on irreversible adiabatic process. The question is given, it will be our question number 4, problem number 4. Two moles of a monoatomic ideal gas initially at 400 Kelvin and 4 atmosphere undergo adiabatic expansion against 1 atmosphere till the volume is doubled. Determine final temperature and work done. Adiabatic expansion against 1 atmosphere indicates that it is a case of irreversible adiabatic expansion, and therefore we'll have to use the relation of irreversible process, that in irreversible process, just now we have seen that P external minus P external into delta V, which is V2 minus V1, is NCV delta T, which is T2 minus T1. Here we'll have to first find out the initial volume, then only we can proceed, since V1 and V2 will have to be used. Let us work out initial volume. So initial volume V1 can be known, it will be nRT1 upon P1, n is 2.082, 400 upon initial pressure 4. So 8.2 into 2, 16.4 liter. So V2 will be 32.8 liter. So if we use that, on left side it will be minus 1 atm into V2 minus V1. So 16.4 liter is equal to, on the right side, N is 2 mole into CV, monoatomic 3/2R, 3/2 into R into T2 minus T1. A very important thing I must bring it in your notice, that here I am writing 3/2 R, and the value of R I am taking 0.082, since on left side we have taken liter atmosphere, so this R must also be in liter atmosphere unit. If we simplify this, what we find, 0.082 into 3.246, 16.4 divided by 0.246, 66.66. So T2 minus T1 is calculated to be minus 66.66, so it can be approximated to be minus 67 Kelvin. So T2 will be T1 plus T1 minus 67. T1 will be positive on right side, and T1 was 400 minus 67, so it is 333 Kelvin. It is the final temperature. Work done, either P external delta V or right side, so work done is minus P external delta V, so minus P external is 1 atm into delta V, 16.2 liter, and if we want to convert it into joule, divide the factor 101.4. 1 liter atmosphere is 101.4 joule. So wait a moment, it will be multiplied, not divided. Multiply it by 101.4. 1 liter atmosphere is this much joule, so this much liter atmosphere will be 16.2 multiplied by 101.4, 1642 minus 1642 joule approximately. So this is the way irreversible adiabatic process differ from a reversible adiabatic process. I recommend you here that you try the same question assuming the process to be reversible. You will find a different value of final temperature and therefore different value of work done. Let us try what the final temperature is coming. This is, I am giving you a work to think that what will be the final temperature had the process been completed reversibly, and then you will find out that where the temperature decreases more in reversible or irreversible adiabatic process if carried out to the same final volume. Let us take one more situation on irreversible adiabatic process. That will be our problem number 5. The question is related to compression, adiabatic compression of a given mole of gas. 6 mole of argon gas, 6 moles of argon gas in a 147.6 liter insulated piston. Insulated piston initially at 300 Kelvin undergo adiabatic compression by applying a constant pressure from outside. A constant pressure from outside until the pressure equilibrium is established and final temperature is found to be 450 Kelvin. 450 Kelvin. Determine work done and external pressure. Two things we have to find out. What is the work done and external pressure. Once again, it is a case of irreversible adiabatic expansion. Irreversible adiabatic expansion. So work done can be determined easily W is delta U and CV delta T. In this case, both initial and final temperature are known, so determining work done is not a big task. N is 6, CV monoatomic 3/2R, and delta T 450 minus 300, 150. So 2, 3, 339, 15, 135, 0 R. This is the work done. Now what to do to determine the external pressure? We'll have to apply the relationship of the irreversible adiabatic process, where P external minus P external V2 minus V1 is equal to NCV T2 minus T1. Substitute volume in terms of pressure and temperature. Take this minus sign inside. So P external, let this be P only. So P, or let it be P external, PE P external into V1 minus V2, and V is equal to nRT by P. So nR will come out T by P. T1 by P1 minus T2 by P2. See, we are taking minus sign inside, so V1 minus V2, V1 for nRT1 by P1, V2 nRT2 by P2. Finally, pressure equilibrium is established, so P external, P2 are same. On the right side, we have N into 3 by 2 R into T2 minus T1 is known. T2 is 450, T1 is 300, so 150, isn't it? So NR cancel off. 150 by 275 into 3, 225. It is 225. On left side we have P external by P1. P1 is P1 initial pressure. We'll have to find out initial pressure. Let us work out initial pressure first. P1 is nRT. N is 6, R is 0.082, T is 300 divided by volume 147.6. So 24.6 into 6, oh, it is 1 atm. So P1, P external by P1, 1 into T1 300 minus P external by P2 1 into T2 450 is equal to 225. So P external will be 450, right side plus 225, 4 to 675 upon 300, it is 2.25 atmosphere. So that is how we work the problems in adiabatic process. So be very careful in solving problems on adiabatic process. Must check the process whether it is occurring reversibly or irreversibly. Otherwise, we may end up with wrong result. So let us take a small part of first law left now, that is enthalpy function. Enthalpy. Enthalpy is a new state function we are going to define in thermodynamics. It is defined mathematically as state function in terms of another state function. It has its mathematical definition: H is equal to U plus PV. Both of these are state functions, so H is also state function. So enthalpy is defined as U plus PV. In physical process, we'll be applying this definition, but we will be taking its more comprehensive meaning in thermochemistry when we'll start studying enthalpy of a reaction. So now limit ourselves to physical processes only. So it is a state function defined in this manner. If we differentiate the two sides, what we observe, dH is equal to du plus P dV plus V dP. If P is constant, dP will be 0. We are putting a condition here. If P pressure is constant, dP will be 0. In that case, dH will become du plus P dV, and if we integrate it, what we obtain, delta H on left side. If we integrate, P we have taken constant, so it will be delta H is equal to delta U plus P delta V. And we have seen in first law that delta U plus P delta V is nothing but Q. Now pressure is constant, so it is QP, and QP is nothing but NCP delta T, and therefore delta H is NCP delta T. So if temperature change is known, enthalpy change can be known, as well as in isothermal process, delta T will be 0, implies delta H will be 0, that is H is constant. So we also call isothermal process as isoenthalpic process. Isoenthalpic means enthalpy does not change. Since H is constant, delta H is 0. So this is the fundamental definition of enthalpy change. It can be known if change in temperature is known, or it can also be known by differentiating this term wise. If we integrating this term wise, so dH is du plus P dV plus V dP. If we integrate it, while integrating the first term, we'll assume pressure is constant. While integrating the second term, we will assume volume is constant. So on integration, what we find, delta H is equal to delta U plus, first pressure is maintained constant, that will be P1 into delta V, then volume is changed, so V2 into delta P. This is another general expression for enthalpy change, which can also be used. So that is the way we define enthalpy change in physical processes. Questions are also asked on enthalpy. in expansion compression process. So let us work out one or two simple questions on enthalpy change. The question is given that will be our question, problem number 6 today. So some ideal gas at 300 Kelvin, some ideal gas at 300 Kelvin, 10 atmosphere pressure, 2.46 liter volume, undergo simultaneous heating and expansion to a final state of 5 atmosphere, final pressure is 5 atmosphere and 6.56 liter volume. Also given delta U, change in internal energy, 30 liter atmosphere. Determine delta H. There are two fundamental ways to attempt this problem. One is delta U is given, so CV can be known, from which Cp can be known, and then delta H can be known. Or we can directly use the relationship that delta H is equal to delta U plus delta of PV, so P2 V2 minus P1 V1. Delta U is 30 liter atmosphere, and delta PV is P2 V2 minus P1 V1. P2 V2 is 5 into this. If we write P2 V2 5 into 6.56 minus P1 V1 10 into 2.46. It is 5 into 6.56, 32.8. It is 32.8 minus 24.6, so 8 minus 6 is 2, 8.2. So it will be 30 plus 8.2, 38.2 liter atmosphere. It can be converted into joule unit by multiplying it with the factor 101.4. There is another approach which can also be used. Delta U is given, and we know that delta U is NCV delta T. Delta U is NCV delta T. If we substitute it here, CV is not known, so CV can be determined. CV can be determined, but for that we'll have to do a lot of calculation. First we'll have to find out number of moles, then we'll have to find out final temperature, then only CV can be known. If we want, we can work out number of mole PV upon RT, pressure is 10, volume is 2.46 upon 0.082 into 300, so it is 1. Final temperature can also be known. T2, PV is equal to nRT, so P2 V2 upon nR. Final pressure is 5. Final volume is 6.56 upon nR. N is 1.082. If we work out, 5 into 6.56 divided by 0.082, it is 400. It is 400. So delta U is 30 liter atmosphere is equal to N is 1 CV into delta T. Delta T is 100. So CV will be 30 upon 100, 0.3 liter atmosphere. It will be per Kelvin per mole also. So Cp is equal to Cv plus R 0.3 plus 0.082. That is very important. It is in liter atmosphere unit. So 0.382. It is Cp. So delta H is NCP delta T. N is 1, Cp is 0.382, delta T is 100. So once again 38.2 liter atmosphere, which is same as we determined here. So that is how we determine the questions based on questions related to enthalpy change. But be very careful when applying this relation delta U from which we find Cv and then we find Cp. All these are true only if the change is occurring on ideal gas, means gas is behaving ideally. But we know from the gaseous state that gas do not always behaves ideally. And we find a question in IIT-JEE 2003 screening in which enthalpy change was to be determined from the given initial and final states, and between the given initial and final states P1 V1 upon T1 was not equal to P2 V2 by T2, means the gas was not ideal, where we could not apply this relationship. The only way is to solve through this. Let us take that situation in fast. That will be our problem number 7 of today. Some amount of gas at initial conditions are given: 5 atmosphere, 10 liter, initial temperature is 500 Kelvin. Undergo change of state to 5 atmosphere, finally to 500 Kelvin, 2 atmosphere and 27 liter. If change in internal energy is 35 liter atmosphere, determine delta H. Ideal condition is not given, so we must check whether P1 V1 upon T1 is equal to P2 V2 upon T2. It is not. P1 V1 upon T1 is not equal to P2 V2 by T2. So gas is non-ideal. That is important. Gas is non-ideal. So what to do? The only way to find out delta H is equal to delta U plus delta of PV. One can try to find out delta U is given, so CV can be known, adding RCP can be known, and from that delta H can be known, but that will be wrong. That will be wrong, because gas is not ideal, so Cp minus Cv will not be R. Simply it can be solved using this, so it will be delta U 35 plus P2 V2 54 minus P1 V1 50. So 4 plus 35, it is 39 liter atmosphere. So this is all about enthalpy change. We'll be doing a lot more on enthalpy change in thermochemistry part, where we'll be solving enthalpy change of a reaction. So today we complete the application of first law to the physical processes. So in the next, which will be our 4th lecture, we'll be doing second law, that is more interesting and more challenging to work out. Second law, the basics of second law, and we'll be defining 2 more state functions of second law, that is entropy and Gibbs free energy, and then at the end we'll be doing thermochemistry part.